The subject today is circular motion. This is our mass, moving in a circular motion, at the same speed, at all times. It is rotating at a constant tangential velocity. What is tangential velocity? At all times the mass is moving in the direction of the vector arrow. If we released the mass at any point, it would fly off in this direction, at a tangent to the circle. What is a tangent? An easy way to remember this is to imagine a T. The top is just touching the circle, tangential to the circle. The bottom runs to the center. The mass always wants to go in this direction, but is held in place on its circular path. So the mass will be accelerating at a constant rate, towards the center at all times. This is called centripetal acceleration. What happens when in a car and it accelerates forwards? You get pushed back into the seat. In circular motion, the pushing back happens in this direction at all times. This is called centrifugal force. This is the force you would feel when on a merry-go-round. If the velocity changes for any reason, the centrifugal force will change. What is a rigid body rotation? It is a physics term for a point or mass rotating about a center point. Translation. Translation, it is simply the movement of the circle's center point. We have already looked at circular motion and the effects on a mass. Adding translation or moving the rotation changes what happens to the mass. This physics works out what is happening. We are looking down on the rotation. There are two velocities to consider for the mass: tangential velocity and translation velocity. As we have done before, both velocities are represented by a vector arrow. You can see the relationship between the arrows. The angle changes constantly. All we need to do now is to add the two vectors together. One at 2 miles per hour for the tangential velocity, and 6 miles per hour for the translation. We will do our vector addition at 4 points. Using top-to-tail addition, we add the vectors. The resultant arrows at each point are our answers. We see that the mass is going from 8 miles per hour at the top, to 6.3, 4, 6.3, and back to 8 miles per hour, on every rotation. This is a constantly changing rate of acceleration.
Okay, so we've got that. Now, so as I'm moving, I can rotate or orbit myself. And again, this is whatever your subject is. Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself. See that? I can rotate or orbit myself. And again, this is whatever your subject is. Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself.
To see what is happening to the mass, we can also use this site's vector addition tool. Input the velocities for each vector. 2 miles per hour, and 6 miles per hour. A plus B, the resultant velocity is the answer for the mass rotating at the same time the rotation moving. Each velocity alone is a constant velocity. When they are both acting on our mass at the same time, the mass's velocity changes. This change is constant. We see an ever-changing rate of acceleration of the mass, going from 8 miles per hour to 4 miles per hour, back to 8, constantly.
Okay, so we've got that. Now, so as I'm moving, I can rotate or orbit myself. And again, this is whatever your subject is. Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself. See that? I can rotate or orbit myself. And again, this is whatever your subject is. Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself.
What has this physics shown us? That a point or mass, on any rotation that is moving, will never be at a constant velocity. The only point ever at a constant is the center of the rotation.
In the heliocentric model of the cosmos, the moon revolves around the Earth 13 times per year, traveling at 2,288 miles per hour, while the Earth revolves around the Sun once per year, traveling at 67,000 miles per hour. The following model and animation illustrate how this is supposed to occur. As you can see, since the moon is revolving around the Earth, which itself is revolving around the Sun, in order to maintain its regular orbit, the moon would have to be constantly and drastically changing its speed in ways completely unaccounted for by the model. In the outer part of its orbit, the moon would have to speed up 67,000 miles per hour, in addition to its regular speed of 2,288 miles per hour, just to keep up with the Earth.
Okay, so we've got that. Now, so as I'm moving, I can rotate or orbit myself. And again, this is whatever your subject is. Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself.
So the moon would then be traveling at 69,288 miles per hour when it reached the front of the Earth. At this point, since the moon is allegedly 240,000 miles away from the Earth would catch up in just 4 hours. So the moon must continue traveling 67,000 miles per hour along Earth's trajectory, while simultaneously continuing its now perpendicular 2,288 mile per hour second trajectory. Then, as it turns to reach the inner part of its orbit, the moon must now slow back down to its original speed, allowing the Earth to pass by.
Okay, So we've got that. Now, so as I'm moving, I can rotate or orbit myself. And again, this is whatever your subject is.
Lastly, as it passes behind the Earth, the Moon must once again quickly accelerate back up to nearly 70,000 miles per hour.
Whatever you're tracking. I just so happen to be tracking myself, so I am orbiting myself.
Before getting left in the dust. In addition to all of this, the Sun itself is allegedly orbiting the Milky Way galaxy at 448,000 miles per hour, further compounding the problems and calculations of the heliocentric model. If this were true, then the Earth, Moon, and other planets would all have yet another set of ridiculous and impossible corkscrewing accelerations and decelerations necessary just to keep up with the Sun. And for the cherry on top, all of these calculations have been assuming perfectly circular orbits, but the actual heliocentric model claims that the Moon's orbit around the Earth's orbit around the Sun, and the Sun's orbit around the Milky Way are all elliptical, not circular, meaning there would be even more additional accelerations and decelerations to calculate depending where each one is along its elliptical path.